Hello everyone, welcome to our group's presentation about data structure Trie. Our group has four members, Lê Nguyễn Anh Khôi, Huỳnh Nguyễn Khánh Duy, Nguyễn Minh Tâm, and Huỳnh Lê Bảo Thùy. Our presentation has four parts. First is introduction, the second is data structures and algorithms. The third is other algorithm, and the fourth is application and risk. Let's come to the first part, introduction. First, about the definition of a tree. A tree, which is called a prefix tree or digital tree, is defined as a tree-based data structure that is used for storing a collection of dynamic strings. About its history, the concept of the tree was first introduced in 1960 by Real de la Gruyendijk in his paper, File Searching Using Variable Length Keys. It became well known after Edward Franklin independently rediscovered and gave it the name tree, which comes from retrieval. Next, we will come to the data structure and algorithm on tree. About data structure, a tree has an empty root node which links to other nodes, and each edge represents a character. Each part from the root to the node represents a prefix or a string stored in the tree. Every node consists of an array of pointers, which its index representing a character and a flag to indicate if any string ends at the current node. Here is the structure of a node in Trie. As you can see, there's an array of pointers to Trie nodes and a Boolean flag to indicate the end of a word. Next, we will come to the basic algorithms on Trie data structure. It consists insert is how to insert a new string to Trie. Is empty to check the Trie is empty or not. Search is how to search for a string in the Trie. Starts with is how to search for a prefix in the tree. Delete node is delete a string from the tree. Deallocated is delete the tree. And the last one is display, is to display words in tree.
Let's talk about the insertion. In insertion, we need to check if the tree is empty or not. If it is empty, we can create a node at the root. But if it is not empty, we need to go to its child and then we can insert the word. But how to do so? Because the tree, it stores the data or the string as each element one by one. So we need to pick up the first one, the second, and from that to the end of the elements. So for example, if we want to insert the word cat into the tree, we go at the root and we check if it is empty or not. Then we insert the word C, A, and T. And T is the end of the word cat, so we make it at the end. Next one, we do so with dot. We have D, O, and G. And remember to mark G as the end of the word. That's all for insertion. For the next one, we have searching. In searching, we also need to check if the tree is empty or not. If it is empty, we return and we set it false because there is nothing to look for. And if it's not, we will traverse the tree like the way we insert a new word. We will go from the root to each child to find the one that we are looking for. And in this case, we need to find the whole word in the tree. It means that we need to reach the end of the word and check if it is true or not. If it is true, then it is the word that we're looking for. And the other case happen when the query and a word is not true, it's false. For example, we look for the word CA. Because CA and this try is not a full word, therefore it returns false. But when we look for cat, we look for CANT, and we know that T is the end of the word. That means that we can find cat as a full word in this example. So next one we have start with. As what you can see on the screen, it is quite similar to the search function. However, instead of looking for the whole word, we just need to look for its prefix, and if all of the elements in the prefix can be found in the try, it means that we can find words that begin with that one and it will turn true. For this example, we need to look for words that starts with CA, and as we can see here, the word cat is beginning with CA, so it returns true. As we mentioned earlier, we need to check if the try is empty or not, and if it is true, it means that the root is not exist. It means that the word is null pointer. However, if it's not empty, we need to check if there is an existence of the other node in the try. And then we have the example, and of course what you can see on the screen, it is not empty because it has two words, which is cat and dog. Then we come to deletion. Try is quite simple, but it is hard to know where to delete. Therefore, we need to divide it into two cases. The first one, we need to know if the end of word is rich. If it's not, we have it in the second case. But in the first case, if the end of word is rich, we just need to unmark it, and we check if there is like no children, because like as you know, a word can be a prefix of another word, so we need to check if there is a children after this end of word node. Okay, so if there is no children, we will delete it, but if it is children after it, so we just need to unmark it as not the end of word anymore. It means that that word is no longer exists in the try. And then if it is not the end of word, as I mentioned before, we need to traverse all its children to get to the end of word, and we do the same as the first case when the end of node is reached. And we need to update the new road if it is possible. So here is what it looked like. We need to delete D in this case, but as you can see on the screen, D is not the end of word. Therefore, we just we didn't do anything, we just skip it. Then when we want to delete dog, we look for D, O, and G. We found that G is the end of word. That means that we will delete it from the back to the front. We delete G, and then O, and then G, and that's it. Root is now only point to cat. And of course, we need to know what is in the try, right? We have display function. Of course, we need to check if it is empty or not, and if we have reached the end of word, because before that we have defined a pointer, or in this case I have defined let me say it is like an array of char. So whenever it is found the next element in the word, it will add to that array, and then after it is finished, it means that it reached the end of work. It will mark the current depth as null pointer, and that is how we find a full word in a try, and we continue until we didn't find anymore. So here's how it works. From the root, we go to find cat. We have C, A, and T. The whole word cat is found, and then we need to print it out if you want. The same thing happened for dog. We go for D, O, and G, and then we just need to print it out on the screen. One of the most important thing for doing this, because we have a lot of pointer in try, so we need to allocate it correctly. In order you want to keep your device safe. So the try is empty, return. If it is not empty, we recursively traverse to each child node, and then we delete it and set it to null pointer. And it's exactly how we do with delete, but yeah, it's much more simple. For example, we want to delete this one or deallocate this tree. We go from C, A, T. That means that we have found all the elements for the word cat, and then we delete it from the back to the front. We have T, A, and C be deleted sequentially, and then we did the same thing for dog. We go from D, O, and G, and then we delete it from G, O, and G. And because all of it nodes, like all of it child node is deleted, then the root node needs to be deleted as well. So yeah, the whole try is deleted. For the complexity, so as you can see on the screen, we have listed out all the functions and the time complexity, as well as the auxiliary space that it takes for this function. I think it is quite simpler to understand all this one, so I just show it here. So yeah, that's all for my part. We will come to the next part.
Let's move to the third part, all the algorithms. Let me introduce the algorithmic algorithm, which is a powerful application of the trie data structure. This algorithm allows us to quickly search for multiple patterns in a text. It was proposed by Alfredo Hall and Margaret Horacic in 1975. On the right, we see the automaton that represent a set of patterns A, AB, BC, BCA, C, and CAA. The blue arrows represents the suffix links, and the green arrows are terminal links. This slide explains how the automaton is built. Transition occur by reading characters and following matching child nodes. If there's no direct transition for character, we use suffix links. These links help recover from mismatches and continue searching efficiently. On the right, we have a table showing which parts are part of the dictionary in the dictionary column, and what the suffix link is, and if they have a dictionary suffix link, which helps identify completon patterns. Next, we have Lampel-Z-Welt algorithm. This reduces file size by replacing repeating sequences with shortened codes, dynamically builds a trie while reading the input text, finding the longest match in the trie.
Now we move to the last part of our presentation. So far we know that a trie is a special kind of tree used to store some data structure, mostly commonly string. This is particularly efficient when many strings share common prefix. And we now move to some key application of trie. Firstly, about autocomplete. Trie is widely used in some search engine, and when a user types a prefix, the trie help quickly retrieve on the word starting with that prefix. Next, about spelling checking. A tree and store dictionary words and check if a given word exists and suggest the correct words. For some misspelled words, similar prefix can be used to suggest correct words by using some fuzzy search. About network routing, a trie can represent IP address and help in finding the longest matching prefix, which is essential in determining routing paths. And about data compression, as we have talked about the algorithm, which is efficient in compressing data. And in bioinformatics, we have some application of trie. As you know, a DNA consists of 4 members, A, C, G, T, which is efficient to use trie to search for the patterns. And some other application of trie, like some dictionary, check if a word is valid in a dictionary which is stored in a trie, and some detection, malware detection, or some file system indexing. Now we move to the last part about quiz. The first question is, what is the primary use of a trie? A. Sorting elements. B. Searching for patterns in a string. C. Searching for a substring. D. Storing string in lexicographical order. The correct answer is B. The second question is, which of the following operations can be performed efficiently using a trie? A. Checking whether a word exists in a list of words. B. Sorting words lexicography. C. Finding the longest common prefix among words. D. All of the above. The correct answer is D. The third question is, what does the count variable in each trie node represent? A. The number of children node. B. The number of words that pass through or end at that node. C. The length of the word stored in the node. D. The frequency of the character in the entire tree. The correct answer is B. The fourth one is, what is the time complexity of inserting a word of length L into a trie? A. O1, B. OL, C. OL square, D. ON, B. OL. The next question is, which of the following is not a typical application of a trie? A. Autocomplete in search engines. B. Prefix by searching. D. Finding the maximum element in a list. D. Spell checking. C. The correct answer. Next, which of the following statement about a trie is true? A. A trie can store both keys and values. B. The trie always use binary trees as structure. C. A trie requires a large amount of memory for storage. D. A trie can only store string of the same length. A is the correct answer. The seventh question is, how do you determine if a word exists in a trie? A. Check if the last character of the word has a count greater than 0. B. Traverse the trie and ensure that each character of the word has a corresponding node. C. Check if a word is present at the root node. D. Check if a word is stored as a leaf node in the trie. B is the correct answer. Next, what is the spike complexity of a trie storing n words of average length L? A O N, B O N times L, C O L, D O N square. B is the correct answer. Next, what is the time complexity of finding on words with a even prefix in a trie? A O1, B OP, where P is the length of the prefix. C ON, where N is the total numbers of words in a trie. D ON times L, where L is the average length of the word. B is the correct answer. The last question is, which of the following operations can be optimized using a trie? Searching for a substring, searching for the longest common prefix, counting the frequency of a character in a string, sorting string lexicography. B is the correct answer. And we represent you some lead call assignments, and you can click on it to practice more about trie. And this is the end of our presentation. Thank you for your listening.